The ability to get the shipper's goods where and when they want them is what we sell. An important ingredient in the expeditious completion of this service is knowing where each railcar is at every point in time. In early 1989, Butch Shadwell of the CSX Logistics Information Systems System Integration Department proposed that given recent advances in machine vision, it could be possible to train a computer to identify rail cars based on their normal appearance. That is, a computer that would find and identify enough important features of car images that it could identify them as well or better than a person. No modification of the fleet would be required.
When the train arrives in the terminal, the conductor carries the information he recorded as to which cars may have been added or deleted from the train to a clerk. His job is to enter the data into the mainframe. Unfortunately, this data entry may be delayed sometimes as much as 8 hours. It's easy to understand that without accurate information on the consist and sequence of cars in a train, efficient switching is impossible. We're currently investigating the use of computer vision to solve this problem. That is real-time identification of rail cars so that we can produce a consist that is accurate and update the mainframe immediately without human intervention. Through my investigation of existing technology, it became clear that the solution to our problem would be advancing the state-of-the-art in machine vision. Through a referral by Dorothy Cranshaw, president of CSX Logistics Information Systems, I made contact with Dr. Robert Thibodeau at Carnegie Mellon University. What drew me to Dr. Thibodeau was his pragmatic approach. He seemed sincerely interested in producing a simple solution that worked, not research for research's sake.
Butch Shadwell started talking to Dr. Robert Thibodeau of Carnegie Mellon University in November of 1989 about enlisting the aid of his department, the Imaging Systems Lab of the Robotics Institute. The working agreement was finalized in June of 1990.
The question that has been put to us is whether or not it's possible to recognize the railway cars. The answer is of course it's possible. Every car will have certain unique characteristics that will distinguish it from any other car, just as a human being has a fingerprint. If you can look at the car finely enough, there will be attributes of that car that are absolutely unique, no matter what. The question we have is not whether it's possible to recognize the railway car, but whether it's a practical thing to recognize the railway car. Can we look at the railway car in detail enough to find those things that make it perfectly unique? We've done this in several areas to ask whether or not it's practical. For example, in one area we looked at electromagnetic signature, and we found that if you put the sensor close enough to recognize the detail of the car, that the sensor would get too close to the car, and so we had a problem of an impractical solution. In the case of scanning the car or taking a picture of a car, you can stand back from the car, and to this date we still believe we have potential for a practical solution for recognizing the individual cars, because we can stand back and yet see fine enough detail on the cars to know that we will be able to catch that fingerprint, catch that signature for the individual car.
Several components comprise the car recognition system. 4 of these, axle spacing, color histograms, roof profiles, and edge profiles, determine the general class of a car. The remaining 2, optical character recognition and feature matching, verify the identity of a specific car. Different car types have different inter-axle distances, which can be measured by a magnetic sensor located on the track. This greatly narrows the range of possible identities for an unfamiliar car. Color is another important cue for distinguishing cars. By looking at all the colors that appear in a sample patch taken from a fixed location on a car, we can determine the major components of the car's coloration. A number is assigned to each color, similar colors are grouped together into bins, shown as cubes in the diagram, and a histogramming technique is used to determine how frequently each color occurs in the image. A third cue to car class is the shape of the roof. Tanker cars have unique roof profiles, making them easily distinguishable. The fourth cue to car class is the car's edge profile. Hopper cars have unique patterns of piping and ladders, making them easily discernible. Edge detection software automatically detects these features in the image. Optical character recognition allows us to read the car ID and number with reasonable accuracy. We have trained a neural network to recognize 26 letters of the alphabet in several fonts. A separate network has been trained to recognize digits. The system has successfully identified the ID number of a boxcar. The first step is to locate the individual digits using edge detection software. These digits are then classified very quickly by the neural network. Because car numbers cannot be read with 100% accuracy, the system also uses other visual cues to identify each car. Such cues include prominent dents and rust spots. In this image, we see a large rust spot on the top of the F and another on the bottom stroke of the E that, along with other image cues, uniquely identify the particular car.
There are a large number of redundant cues available to us for recognizing a car. Axle spacing, car height, roof and edge profiles, color, rust spots and dents that are unique to each car. We can apply optical character recognition to read the car ID and number, and in cases where those aren't readable, we can at least recognize the shapes of the letters. Given the large amount of redundant information, we now feel there's a 65 to 75% probability of success for this project.
We're attempting to disprove the hypothesis in steps. The first step is, can you show that you can in fact recognize the cars? We're showing that you can in fact recognize the cars with our software. The second one is, can you build a scanner that you can deploy out in the field that allows you to recognize the cars? And the activity we're currently engaged in, should have completed before the end of the year, is the construction of the scanner that is a deployable scanner for which we can use to recognize these cars. The last step is, can you show me some cars you can't recognize? We're deploying the scanner in order to take hundreds, thousands, if not tens of thousands of images of cars to find those situations where we may be able to show that we cannot recognize those cars. Okay? If at the end of this process we can't show any situations that we can't recognize the cars in, we will have deployable prototypes, deployable scanners that will recognize cars.
CSX is taking the lead in advancing automation of inventory control. It's clear this will impact the entire transportation industry. Containerized freight, tractor trailers, and fleet vehicles of all kinds will benefit. At this point, the prospects are exciting.